So this next section is going to be all about inequalities. Before we can actually talk about solving those inequalities, we want to see how can we represent an interval as a solution to something. So if you know your variable is trapped between two numbers or has to satisfy at least one of these intervals, how do you go about writing it? So we have a couple different ways. First one is inequality notation, which is going to be what you typically get for those solutions. So here we have a particular inequality, and this is going to be read all values of x greater than or equal to a, but less than b. So that means I can equal a, but not equal b. So these bars underneath will indicate whether or not you have equality at that endpoint. The second one is a graph or a number line. So if we use this exact same inequality, a can be included, but b cannot, so that's excluded. So we can create two different number lines from this. So either one is going to be fine, but you have two important points, A and B. So we'll draw those in. And then here you can equal A, so we can put a closed circle, but not B, so it's an open circle. But then anything in between is perfectly fine. Likewise, another way you could do that, which will help with our interval notation soon, is you can put a square bracket around this, kind of like the sharp edges of an equal sign. And then you put a parenthesis here to say you can't equal this endpoint. And then everything in between is okay. This next way, the solution set, is going to be a little bit complicated, but it's going to have value to it for future purposes. So what this does is it tells you to take all values of x, this bar is going to mean such that, and then you put whatever conditions you want to hold over here. So this is specifically read all values of x such that x is greater than or equal to a, but less than b. So if you had more conditions, it would go over in that right-hand side after the bar. Now, interval notation is going to be our most common form that we're definitely going to use more often than the others. So it condenses everything. You don't have a variable, but any values in between these are going to be good. So based on the bracket or parenthesis you put, it tells you what happens at the end point. So a square bracket means you can actually equal it, while parenthesis means you have to exclude it. So you can get very, 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 very close to the number, but not equal it. So in the case, if you can keep going on forever, you're going to tend out to positive infinity or negative infinity. You're never actually able to equal those, so you need to make sure you put an open parenthesis around an infinity. So let's get some examples, and we're just going to rewrite in interval notation, and then we're going to graph the point. So x has to be trapped between -4 and 1, and we can equal both of those endpoints. So we put square brackets around -4 and 1. To graph this, we'll go ahead and put -4 and -1 there. You can equal both of those endpoints, and then you can hit everything in between. So make sure you just make a good distinction between a closed circle and an open circle. For this next one, you can satisfy either one of these equations. So for this next one, either interval can be satisfied for it to work. So x could possibly be greater than -3, or it can be less than or equal to 7. So to write this in interval notation, it's going to be easier to actually go ahead and graph it first. So we've got -7 and -3. -7 is going to be the lower point, so it goes on the left. So our first interval tells us x is strictly greater than -3. So I have an open circle there, but I can equal anything to the right. The second one tells us x can equal -7, and anything less than that is also fine. So since I have two different intervals, I need to join them together. And so what we're going to write is we can start at -infinity, go to -7, or we can go from -3 up to positive infinity. So the symbol in the middle is our union symbol, which also means or. Okay. So we have two operations that look similar to each other. The U is the union of two sets A and B. What this does is as long as it's in one of them, it's in the union. It's the members of A, members in B, or members in both. So I kind of think of these as cups. The cup being up means you fill it up. Keep filling it up. It's less restrictive. Lots of stuff can go in. The intersection is going to be the closed cup. So it's kind of like you don't want to put anything else. It's going to be more selective. So that's exactly where those two overlap. It's members that are common to the two sets. So let's look at some examples. Let's write as a single interval and go ahead and graph it. So what I want to do in each of these instances, we've got two intervals that we're combining. I'm going to go ahead and draw each of them. And then I'm going to draw one more to represent my final thing after the operation. So this will be the interval 2, 7. This will be the interval -5, 3. And then this one will be the actual union between these two. So I have 4 important numbers, so I want to make sure I'm including them on all of the different intervals. And so we've got to put them in numerical order. So -5 is our lowest point, then 2, 3, 7. So I'm going to write them on all of these. So for my first one, I can't equal 2 and I can't equal 7, but anything in between is going to be good. For the next one, I can equal -5, but not -3. But anything in between is going to be good. Now for the union, as long as it's in one of these two, it's in the union. So if we look down, nothing is over here, so I can't have that in my union. If I look down at 5, that's in this one, so it's going to be in my union. Same thing with 2, it's at least in the middle one, so it's in the union. 3's in the first, so it's in the union. 7's not in either of these, but it's still kind of important, so I'm going to bring that open circle. And then for everything in between, it's in at least one of those sets. So the union of these two is starting at -5 up to 7, can equal -5, but not 7. Okay. For our intersection, same thing, but now I just have to be selective with that end operation. So we're going to draw 2 number lines for each interval, and then we're going to go ahead and we're going to look at the intersection. So we're going to plot -5, 8, -infinity to -6, and then we're going to see what is in common to these two with the intersection. So we really only have 2 numbers, -5 and -6. -6 comes first on this number line. And so for our first one, we start at -5. We go out to positive infinity, can't equal -5. Second one, I can equal -6, and then it's anything less than that. And if we try to see if there's anything in common between the two, there's nothing. So because of this, the intersection we say is equal to the empty set. So because of this, we say their intersection is equal to the empty set, which is denoted by this symbol. Or you can also call it the null set, but there is zilch nothing in common to the two. So now we can utilize this idea to actually solve some linear inequalities. Now you're not going to have just a single solution, you're going to have an interval, and any value in those intervals will satisfy it. So you can use the same techniques from solving our equations before, but you just have to be careful if you multiply or divide by negative numbers. It's going to end up flipping that sign. So let's do some examples. Let's solve each and state the answer in interval notation. So first and foremost, the thing I need to do is solve for x, so I ultimately want to isolate it. So let's go ahead and distribute this -3. So that's going to give us -6 minus 3x. Now we can combine our constant terms. So we get 4 minus 6 is -2. Bring the 2 over to the other side. And so we get -3x is less than 7. So dividing by -3 will give us our solution values for x. But because we're dividing by a negative sign, we have to remember to flip the sign. So this gives us x is greater than -7/3. So in interval notation, you start at -7/3, and you can go anything higher than that, so you can go to infinity. So in this next problem, we have quite a lot going on, and we have a lot of fractions. So what I'm going to try to do is I'm going to wipe the fractions. So all of them are just constants, which is fine. So if we go ahead and multiply by the LCD, which is 12, I can go ahead and wipe every single fraction we see. So if you distribute the 12 out in the first fraction, 12/2 will be 6. In the second fraction, 12/3 will be 4. So you distribute a 4 out. X/4 times 12 will be 3x. And then 12/12 just becomes 1. So now I've simplified this. Go ahead and distribute that -4 and solve for x. So you need to combine those a little bit first because you can have some like terms. The 6x minus 4x is 2x. Now you need to move all the x's to one side, constants to the other. Doesn't matter which way you do it. But I'll go ahead and move this 2x over here so I can keep the x positive. So by doing that and adding the one to the other, we'll get 13 is greater than x. So x has to be less than 13. So anything lower than that is good. So from -infinity up to 13. So the very last thing we want to go through is about polynomial and rational inequalities. So these ones you have to be a little bit careful with. So we're going to have a similar approach to both of them. So the best thing we can do is by example. Let's solve and express the solution in interval notation. First and foremost, every single one of these, move all the terms to one side. So I'm going to move the 15 over to get x squared minus 2x minus 15 is greater than or equal to 0. Now I want to go ahead and I want to find the values of x that make this exactly equal to 0. So set it equal to 0, factor, you find two values that this will happen for. Now I'm going to create a number line using these 2 points as our key points. And then we're going to go ahead and we're going to test to see if that specific interval is going to work. So I've got 2 important points. One of them is -3. One of them is going to be 5. I'm going to go ahead and label these as interval 1, 2, and 3. If we want to go ahead and see if each one's going to work, we're going to pick something inside each of them. So inside interval 1, you could pick -4. And plugging that into any of the inequalities you have. So we have, if we go back a little bit, the inequality we're working with is x squared minus 2x is greater than or equal to 15. So if we plug in -4, we get -4 squared minus 2 times -4. That's 16 plus 8. We want it to be greater than or equal to 15. This is definitely good. So that tells me the stuff inside interval 1 is going to work. Now if we move on to something in interval 2, 0 falls in there. So if you plug in 0, you get 0 squared minus 2 times 0. That's just 0. You want this to be greater than or equal to 15, which definitely is not the case. So this interval is not going to work. Finally, you pick something from interval 3, say 6. So that gives you 6 squared minus 2 times 6, which is 36 minus 12. We want this to be greater than or equal to 15, and that's definitely a true statement. Okay. Now we need to check, do I have closed circles or open circles at these endpoints? So let's test our endpoints. If you plug in x equals -3, that gives you -3 squared minus 2 times -3. So 9 plus 6, which is 15. That's definitely greater than or equal to 15. So I can actually equal this point. It's going to be the same thing for 5. You're going to get 5 squared minus 2 times 5. So 25 minus 10, which is 15. So in this case, this endpoint also works. So we really get two solutions, or two intervals that will satisfy this inequality. Interval 1 works, which is from -infinity to -3, and I can equal this point. And then from 5, we can go on to infinity. Now, if instead we had changed this problem just slightly to strict inequality, all that would have done is made these 2 points we found not be solutions. So really you can also just kind of check based on the equation itself if you can equal the endpoints. So in the case of strict inequality, you'd have parentheses around -3 and 5. Okay. Now the last example we're going to go through, there's a really common thing that you're going to want to do and you need to avoid doing it with all costs. So we've got this expression here. I know we hate fractions and we want to go ahead and solve this like we're used to, but we have a bit of a problem. You cannot multiply by that denominator. I cannot actually get rid of these fractions because I don't know anything about this expression 4 minus t. So you have to be careful. Don't cross multiply. I don't know if this is positive or if it's negative. T is varying. If t is 0, 4 minus t is positive. So multiplying by 4 wouldn't be a big deal. But if t is 5, the bottom's going to be -1, you'd have to switch your signs. So never, ever, ever, ever multiply an inequality by a variable. Instead, you follow the same approach as the polynomial inequality. Move everything you can to one side. Make a single fraction. So starting with this, I'm going to go ahead and subtract the t, and I want to combine it to a single fraction. So I want to go through and multiply by this common denominator of 4 minus t over 4 minus t. So when we do that, we can combine it to a single fraction. Go ahead and distribute that -t. Nice things happen, and the t squareds cancel. So you just get -6t over 4 minus t is greater than or equal to 0. Now to break your number line down, you want to find the values that make the numerator 0 and the values that make the denominator 0. So -6t equaling 0 means one important number is going to be t0. And then 4 minus t equaling 0 tells you t equals 4 is another important value. So you're going to choose these numbers as your important ones to break your number line down into an interval test. So I've got our simplified expression here that I'm going to use to test my interval. I've got 0 and 4 as our important points. So I'll call this interval 1, 2, and 3. If we want to go ahead and we want to look at those endpoints first in this time, if you plug in t equals 0, you get 0 over 0 is greater than 0, so you can actually equal this point. If you go ahead and try to plug in the other one, t equals 4, that causes a problem because you're going to try to divide by 0. So I can't actually equal this. I have an open circle here instead. So now we can go through and test each one separately. From interval 1, we could pick t equals -1. Plugging that in gives you 6 times negative 1 over 4 minus negative 1. So that becomes 6 over 5, and that's definitely greater than or equal to 0. So interval 1 is going to be good. For interval 2, we could pick positive 1, and that's going to give us negative 6 over 3 is greater than or equal to 0, and that does not work because we get a negative number. Then if we pick something in interval 4, like 5, we'll get negative 6 times 5 over 4 minus 5. So you get a negative over a negative, which is a positive. So this interval also works. So interval 1 and interval 3 are both going to be good. I can equal 0. I can't equal 4. So our solution is from negative infinity to 0, and then from 4 to infinity.